Philip's not here.
He's not.
Let's start. So, welcome to Model Theory Seminar. I'm happy to introduce Reid Dale. We'll be continuing to speak upon Pillay's Galois theory.
Great. Thank you, Alf, and thank you for organizing the Model Theory Seminar. So this talk is a continuation of the one that finished about 45 minutes ago. And the general idea, if you weren't there, is that we want to understand Coultron's Galois theory using the machinery of model theoretic Galois groups called binding groups. And I guess the main theorem that we talked about last time is the following. So if T is a totally transcendental theory with elimination of imaginaries, and X, Y, X is internal to Y, and models T is the prime model, then there exists a definable group G, definable over the empty set, such that its endpoints are, we can think of as exactly the automorphisms of M, fixing the y points of M, or the endpoints of Y, restricted to X. And to recap, the domain of this group is just the type of some fundamental set of solutions over the empty set. In this case, when I say over the empty set, I'm assuming that T already contains all the parameters that we use. So for instance, the theory T that we're looking at is typically going to be DCF 0M containing a given differential field. And now each element of F is named in the constants, and we don't need to add anything else to look at the type. Oh, but we should look at the y points. Sorry. So the domain of our group is this type, which because M is a prime model, this is in fact a definable set, which I call fund x0. The type of this is atomic. The type of x naught over ym is isolated, and hence it's a definable set. Yeah. In general, you won't get that that's a definable set, but instead a type definable set. And how did we get the multiplication? Well, we used the fact that we had a witness to internality, which gave us this map from y to some power m times the fundamental sets of solutions back into the set of fundamental sets of solutions conjugate to x naught. And we used u to define multiplication. So if I had two elements y1 and y2, I guess assuming by replacing with the quotient, we'll just assume that this map on fibers is injective. Then how we defined y1 and y2 was the unique such that u of y1 x0 equals, sorry, u y3 x0 equals u y1 of u y2 of x0. And then with this definable group operation, we could realize this automorphism set as being isomorphic as an abstract group to this definable set, and in a unique way. So this is a very quick recap of the previous talk. And so now, what does this have to do with Galois theory? And we talked a bit about the Carvesio case in the previous talk. And let's just spell out that example once more. But in the case where we take T to be DCF 0, 1, F, and X to be the zero set of L, an order n linear operator, Y to be the constants, and I guess X naught to be any C basis of ZL. Then the binding group bind X, Y. Oh, and I forgot to say what U is, but U is the function that takes some n tuple and our fundamental system of solutions conjugate to X naught, and returns U of C alpha equals the sum Ci alpha. And with all this information, what we conclude is that if K is a Picard-Messier extension for L, then the binding group.
So I think X naught should be alpha.
Yes. Thanks. Then find x, y, u alpha is just the Galois group, the differential Galois group of K over F. And the way we see that is, well, so an automorphism of the differential closure fixing the constants together with all these parameters F. Well, since I guess we assume that the constants of F are already algebraically closed, so all we're asking is that the automorphism fixes F. And we're looking at automorphisms of the differential closure restricted to R0 set. But then what determines such an automorphism? The image of alpha under it. And that's precisely what determines an element in the differential Galois group of K. So that's this identification. So our goal is to come up with a definition of generalized strongly normal extension that where the Galois groups are represented by binding groups, and such that every strongly normal extension is a generalized strongly normal extension. And moreover, we're going to have a Galois correspondence and other nice properties. And we'll be able to characterize precisely what these generalized strongly normal extensions are, at least in the ordinary case. So that's a roadmap. I'll call them generalized strongly normal extensions. And then talk about the Galois correspondence. And then we'll finally relate them to logarithmic equations. And this last step will involve a certain structure theorem about differential algebraic groups of finite dimension. So that's the plan. So the definition that Pillay came up with is sort of a reasonably straightforward generalization of Colchin's original definition of a strongly normal extension. So everything's in the context of DC of 0, or really it can also be in DC of 0 M, so you can allow M commuting derivations. Just as far as understanding the definitions, everything will work will work in either case. So let F be a delta field, X be a set definable in DC of 0 M F. And we're going to, I guess here K will be a differential field sitting inside the differential closure, but containing F. So this hypothesis isn't quite necessary. We talked a bit about this in the Picard-Vestio setting in our last meeting, and conditions about internality will guarantee that any such K will live in the differential closure A, but to simplify the presentation, assume that we have some field K sitting inside the differential closure. Then we say that K is X strongly normal, provided, first of all, the F points of X are the same as the F hat points of X. So this is analogous to the no new constants.
Should you point out that the Y
Yes.
the example is the X?
Actually, yeah. I mean, how about I just even start over? And everything will be a Y strongly normal set. Tell me if I mess up, but I should be talking about Y. So the point here is that Y is going to take the place of C in all the examples that we've looked at before. So this is the set that is going to help us cover whatever geometric object we're going to look at. So, so the first is that you have no new Y planes. The second condition is that K is differentially finitely generated over F. So for alpha, for some finite alpha, inside the differential closure. And finally, a normality condition. So for any embedding of K into some universal differentially closed field, U, we have that it lives inside a certain small part of the universe. So, so the image of K under sigma lives inside the differential field generated by K together with the U points of Y. So again, if you take Y to be the constants, this is again Colgin strongly normal. That's the definition.
You mean some cap delta?
Yeah, sub delta. All right, and so so we have this. So we have a essentially a no new constants condition, a finiteness condition, and a normality condition. Now, the point is to construct associate to this datum a binding group that that we can call just the Galois group. I mean, if we just take our definition to be of our Galois group to be the set of automorphism, a differential automorphisms in K fixing F, we want our binding group to be exactly that.
Even though sigma takes K out of K?
Oh, sorry. Nope. We want this to be yes. Sorry. So we want a binding group that is iso to this Galois group that appears in the usual strongly normal setting. And so, what we learned from the last talk is that if we want to construct a binding group, we need to be able to find internality data, right? So our goal is to use this definition that ostensibly mirrors Colchin's definition of a strongly normal extension and use it to construct some internality structure that will give us this group. So goal. Use structure of Y strongly normal extension to get internality. And here's how we're going to do it. By definition, we have that K is generated by some finite tuple alpha, right? And so what we're going to try to look at is the type of alpha over, in this case, the empty set. Then this formula, then because we're in a differential closure, this is isolated. And so we're going to look at the fundamental set of, all right, so this type we're going to call the fundamental set of alpha. Now, if beta is in this set, of course, we have some sigma, I guess some automorphism sigma such that in auto f hat fixing f so that sigma of alpha equals beta. Right? So this is just unwinding.
So beta is a set of formulas?
No, beta is a
What's
fundamental set.
What's the type?
Okay, so what I wrote was, I was thinking of the type as itself a subset of the universe. Just namely, all the things that satisfy the same,
Oh, you mean
the same conditions as alpha. But then that is itself a definable set, because it's
you mean
it's
what we
constrained.
might call the solution set of the set of formulas?
Yeah, so this is just a, I mean, think of it like if you have an infinite set of conditions, this is the set of all things satisfying those infinitely many conditions. But because alpha is constrained in Coltrane sense, we can reduce that to a finite set. Yeah, so this is the same business. In other words, this type is isolated by a single formula, so we can replace this infinite conjunction of Coltrane constructible sets with a single one.
But you're looking at the definable set. Was that definable by the type?
By the.
Yeah, he's looking, the fund alpha is the set defined by that type.
Oh,
Yeah,
okay.
yeah.
Oh, okay.
Yeah. That's what fund alpha is. Yeah. It's a set defined
Yeah,
by
sure.
Yeah.
Yeah, sorry. Yeah.
Yeah.
Okay, right.
So now, so sigma alpha equals beta, which, but sigma in here has to map into the set defined by the y's. So this lives inside k delta y, right? So now, what does that mean? So we have that we can write sigma alpha as some function f applied to alpha, where f is a rational function, I guess differential rational, right, over and so this is the analog of when we look at the Picard-Passio case. When we hit our basis with an automorphism, then its image is expressible as a linear combination of constants in that same basis. Right? So this is a straightforward generalization of that phenomenon that we saw in the Picard-Passio case.
Doesn't put beta into k y of f hat?
Yes, it does.
It does.
Yes.
Oh, okay.
Yes.
Which is the same as y of x, right?
Which is the same as.
Which is the same as y of x.
That's what I was going to ask. Does this reduce to automorphism? Yes.
Yes.
Okay. Yeah.
By our assumption. Yes.
Right.
Yes. And so we express the image of alpha as some delta rational function over f
Right.
in terms of alpha. Right? And so now, what this tells us is that, I guess how do I want to say this? So, in other words, so for all elements beta in fund alpha, there exists some definable function f beta such that, definable in other words, delta rational over f, such that beta equals f beta of alpha. And now, by compactness, we were able to reduce to finitely many such f's. So there exists f1 through fn, say, such that for all beta in one of So fi beta, fi alpha equals beta for some beta. Or for some I. So, so justify this normality condition, where we can express the image of any automorphism as some definable function in terms of that parameter. By compactness, we can reduce it using only finitely many such functions. But then, by coding together these functions, so we can realize fund alpha as being internal to y, because the arguments here were rational function, delta rational functions, I guess, over points in yf. And so now, using f, we can realize fund alpha as being internal to y, because we had, I guess we can call our function f hat. F hat goes from, I guess, so these might involve many parameters from y, but there are only finitely many functions, so there's only finitely many y's we can use. So there will be some n such that each of the fi's only uses at most n elements from y, together with a single point in alpha, say fund alpha, mapping back to fund alpha. And alpha is going to be itself a fundamental solution for this function f. So to recap, just using the definition of a generalized strongly normal extension, well, we used, our goal was using this normality condition, we were able to get this type internal to the y points of f hat. But now, using part one, we were able to get it down to being internal to just the f points of y. And then, finally, the reason that we could get off the ground was because we're looking at the type of some finite tuple, alpha, which generates our set in the first place. So, putting this all together, we're able to conclude that, I guess, fund alpha is internal to y via f hat. And then this gives us a binding group. So corollary, we have the binding group. Bind fund alpha y f hat alpha. So now by the exact same argument as in the case of the Caravestio extensions, this type, the type of alpha, exactly is in one-to-one correspondence with the automorphisms of K, fixing the differential automorphisms of K, fixing F, because such an automorphism is determined by its image on alpha. So we can conclude that if K is a Y strongly normal extension, of f, then the Galois group of k over f can be equipped with the structure of a group definable in Y. And here, we can take all the parameters to be in Y, and the multiplication will only be in parameters in Y. Again, this is for the same reason that in the Carvesio case, we got an algebraic group. By in a stable theory, any definable, I guess any subset is stably embedded, and in particular, the set Y is stably embedded. So once we're able to define multiplication on our group G alpha, I guess I'll call it, because these are all subsets of some power of Y, we can define the multiplication as such. But it might have more structure than in the constant case, because if Y has some non-constant points, then more exotic structure may arise.
Differential algebraic group?
Yes, it is a differential algebraic group, because we started off in DCF0M, right? And any group definable in DCF0M is a Colchin constructible differential algebraic group, but really the category is equivalent by the same Weil-style argument to the category of algebraic groups. So, yes.
Algebraic group?
Or of differential algebraic groups. Sorry.
My whole career.
So if you take delta and partition it into a delta 1 union, disjoint union delta 2, wouldn't this incorporate the parametric, or generalize the parametric precognition exception?
Yes, this is done. So, okay.
Yeah.
What about the problem of the differential closure? If you take the differential closure with respect to all of the operators, or the differential closure with respect to the parametric?
Yes, we do exactly that.
The parametric? Yeah. So there's a problem of embedding differential closures with respect to what subset of operators into differential closure, or the reverse.
If there was whatever y involved, the delta that y was involved with.
Though you still,
No, y is the big delta in the parametric theory, isn't it? Or is it?
No, y is
No,
the parametric delta.
Yes.
Y is defined by the parametric delta.
You have to specify.
Yeah, just specify that.
Yeah.
Not specify.
But here is general enough that you don't care about
Yeah, exactly.
That's right.
partition.
yeah. And so, I mean, I guess in the,
Just defined over the subs.
You can take it as,
parametric
you can take the parametric thing as an example where this thing fit. You can fit it into.
No, but the automorphisms have to commute with all the operators, not just the parametric. In other words, the
Right,
structure
okay.
of
Yes.
the extension involves.
Yeah, that's a little subtle point. I don't know
Yeah,
how this-
that's.
I think
the
that-
problem I have.
I think that's fine in the binding group example, because, I mean, so I don't know that much about the parametric example,
Yeah,
but
because you-
This is work of like working the X strong monomers,
Yeah,
the Y
yeah,
strong monomers, that's
yeah.
done by Omar. It's
Okay.
easy sort of thing.
I mean,
By Omar.
once you fix the number of derivations, then any such automorphism in this sense, I mean, we're looking at automorphisms of the structure, which means that automatically it has to commute with all m derivations.
Right.
Right.
So that's already encapsulated in the binding group construction.
Right.
And then,
But
Yeah.
what about the definition of Y? A priori, just looking at this, seem to involve all the deltas.
Well, yes.
well,
you can
I mean,
say it
this is
involved,
just very general.
but then something
Yeah.
doesn't happen.
Yeah. So I mean, so for instance, your y could be the constants in the delta 1 constants.
Exactly.
For
Well,
instance.
yes, but,
And then you're still going to look only at the automorphisms
Oh,
that
okay.
commute with all of them, but you're looking at the ones that are parameterized by the delta 1 constants. Yeah. So that's I think how it fits in. Is that because
I might
if you're
have a Y
interested,
that doesn't involve the parametric derivations at all, under this definition.
what do you mean?
Just if you take any subset of the set of derivation operators, they will define a big delta set.
Sure. Yes.
But I might not use any of the parametric derivations.
Oh, yeah.
to define
And
Y.
that's fine because
Fine.
remember
Y
because
could be just an algebraic objects, basically.
Yeah.
Not in the parametric theory.
No, you could
Why not?
make it fit.
It has to be defined by just the operators that
Yeah.
are parameters. If you have, say,
So you
say
can
partial
type an
x,
algebraic.
partial x might be the Galois theoretic derivation, and the parametric space would be defined by partial t alone.
Yeah, and that's okay. I think
So it's
the-
not specified here.
No, because this is
It's
very
more
flexible.
general.
The point is that once you,
General.
if you're looking at, I mean, I guess one thing that I should really note is that under this, assuming the first two hypotheses, being internal to y is the same as this condition. These are equivalent. Because if you're internal, then you always have a sort of f rational function using parameters from y to get you in here. So that's good.
What we would emphasize is that sigma adds only the constants of the Galois theoretic derivation, which are functions
and that's
of
fine.
t.
Yeah, and so the point is that if you're when you
That doesn't
work with
say
it,
that. Does it?
You would have to make y fit.
fit into
You have
this.
to, yeah, so you'd have to change it, tweak it a
Yeah.
bit.
Yeah, and so the point is that, but if you can, so even if this presentation might make it look more difficult, this is equivalent to internality. So if you can exhibit this parameterization, then you automatically satisfy this. Yeah, a priori, this is the harder condition to satisfy because you might, or going from here to internality is harder because you have to invoke compactness to get finitely many things. But if you already have internality, you're already in this setting, and you can then apply binding loop constructions to it. So the whole point is that if you're in a situation where you have internality, then you're in this generalized strongly normal setting. So if you have internality to some to the constants of some parametrizing set of derivations,
Right,
then you're good.
then you're okay.
So that's the point. This is very flexible, and you just choose the y according to the situation that you're in.
But the Galois group may not be the same as the parametric Galois group in that case.
So what's the definition of the parametric Galois group?
It's the group of, actually,
It's the
it's the
what we
group
call delta
of
prime.
automorphisms
differential
of the
degree.
extension with respect to all the operators.
Which is the same thing as
The
this.
condition that it only, in culture setting where you do isomorphisms first, and then, that it adjoins to the original extension only constants of the Galois theoretic derivations, in other words, functions of t, of the t's instead of the x's. So there's a
Which one is your
condition
problem?
that
T is your problem?
that it might go out of the field a priori, but it only adds constants of the Galois theoretic derivation.
Which is this condition. That's exactly this condition. You go outside of k, but only insofar as you're adding these Galois derivations. That's what y. You take y to be the set of constants in that.
Yeah, it is the set of,
Your subcapital delta is the full delta.
Yes, that's what you
That's
want.
the point.
that's
Yeah,
okay.
that's what you want.
But you just add the constants of the Galois derivation, say there's
Yeah.
only one, the Galois derivation.
Yeah.
And it's, what it talks about are linear differential operators whose coefficients, say in d sub x, whose coefficients involve both t and x, so they're not autonomous.
Mm-hmm. Yeah, I mean, from this discussion,
Got that t in there.
I'm pretty sure that by
Yeah.
selecting y to be the constants of some of the set of derivations, you are getting the same
Except
thing.
this condition doesn't say that.
No, because you don't see it, because the y here is you don't see the condition in y here.
No,
But if you choose the
If
y,
you choose the y to be that, then the solution space is internal to that y.
I see, so you just make the whole theory, we're going to assume in
Yeah,
the beginning
yeah.
of this.
So in this case,
join
yeah.
functions of t of the parameters.
Yeah, so if you start off with this set of solutions to your differential equations parameterized by these other derivations, right?
Right.
Then the constants of those other derivations, your solution space is internal to it, which puts it in this framework. Yeah, I mean, would you agree, Ronnie? Yeah. Anyways, so we get this binding group, and so using this binding group, you get a Galois correspondence. Namely, I guess if you have K and X or Y strongly normal X of F, and I guess with binding group G, and for L, an intermediate differential field between K and F. We set G sub L just to be the set of G and G, such that for all elements of L, G of C equals C. Okay? And then the first condition, or the first thing is that K is Y strongly normal over L as well. Not hard to see. The second condition is that G sub L is
Do you have the K mu?
No.
No?
No,
Okay.
K is bigger than
The
L.
top-
Oh, okay,
top one.
okay, sorry.
Yeah. Yeah, K is on top,
Yeah.
F is on bottom, L is in the middle. Yep. And so then GL is an F definable subgroup of G.
So you don't mean isomorphic? Okay, all right, subgroup, sorry.
Yeah, it's a subgroup. Yeah, G sub L is a set of all elements fixing everything out, right? And then assignment L to GL is a bijective correspondence between finitely generated intermediate subfields. Finitely generated.
Are you in category 0, right?
Yes, and but the proof of so the reason I highlight this is because the proof that a subfield of finitely generated subfield is very difficult. And so I point this out because if you, it's not too hard to see using model theory that if you are inside a extension, then a subfield has to be finitely differentially generated because of a nice stabilizing condition. It follows from the correspondence. Every subfield is finite, or every differential subfield is finitely differentially generated. So I highlight that just because it's
Okay.
a nice consequence. But yeah, so I mean, it really is just intermediate differential subfields and they are, yes.
But they are,
Yes,
in general.
but that's hard. So the reason I point out is just because it's harder. It's more difficult to prove.
He's using model theory to prove that it's finely generated and everything,
Yeah,
as a corollary, basically.
yeah. So I guess what I should say is that if you do everything, you can do everything that I've said at the level of you can start with infinite tuples generating your field extension and type definable groups. So groups defined by infinitely many conditions. And then you can develop a Galois theory or Galois corresponds for that. But then on the group theoretic side, any infinite descending chain of differential algebraic groups stabilizes. And which, on the other hand, will mean that once you have to do a little bit of argument, but that'll mean that you have a finite generating set for the field. So there's a nice Galois theoretic proof of that in the case that you're contained inside some strongly normal extension. That's all I wanted to point out.
Yeah, I see, yes.
Yeah. So you don't have to do a lot of, I think the argument for this is a lot of difficult algebraic geometry in general, right? Or what's the, to get that every differential subfield is finally generated?
Because you don't have Galois theory.
Right, because you don't have a Galois theory. Yeah.
Every intermediate differential field, subfield of a finitely differentially generated extension of a differential field is also finitely differentially
That's
generated.
hard to prove, you're saying.
Culture proved that.
Yeah.
That's in general, that doesn't.
Yeah, but that's a harder proof.
That's hard to prove.
This is just a straightforward Galois.
Here is using
Galois.
compactness to prove.
Yeah, but
Yeah.
I want want to be sure to emphasize that isn't
It's always true. Yeah.
only
It's always
true for strong, it's not only
Right.
true here. It's true
Right.
for every finitely differentially generated. The big
Right.
problem is trying to get the ring of invariance finitely differentially generated.
I see. Okay.
Yeah, that's very different.
Yeah. Anyway, so this is a bijective correspondence
Right, that's not, yeah,
between intermediate subfields and differential algebraic subgroups.
right.
And I mean, you, given a subgroup of G, look at the fixed field. So that's the bijective correspondence. And then you have that L is strongly normal over F if and only if the Galois group is a normal subgroup of G. So the usual Galois correspondence goes through. And the proofs, I mean, really the proofs aren't too bad. I guess you can see that this is, yeah, okay. In any case, the last thing I wanted to talk about, so you get this nice correspondence. The last thing I wanted to talk about is precisely what field extensions are y strongly normal for some y. So characterizing y strongly normal extensions.
Well, that would be for some given block, not
Or for generalized, yeah, okay.
Okay.
So for generalized strongly normal extensions. And so we'll show that, I mean, the result is that any generalized strongly normal extension is a generalized strongly normal extension for a very special y, for a very special type of equation. Yeah, and this is where these logarithmic differential equations for algebraic D groups come in. And so there's a result that I really don't want to talk about, but I'll explain just a bit of how you get the groups involved here. So,
So with all the differential with subgroups of GM, some power in here?
yeah, I think that it is equivalent. I think that you can always, I don't know over like I don't know if you can always do it over Q or CT or something, but there always will exist a pair witnessing some given differential algebraic subgroup. Yeah, but
You can't do it over a CUT X, for example,
Famous result?
yeah, and so
necessarily if it's GA, you're trying to realize GA.
yeah, okay, and so so basically the result is that if K over F is generalized strongly normal, then K equals, so I'm only going to work in the ordinary case right now.
Sure.
So provided that the Galois group is of finite differential dimension, then it will be equal to it will be generated by a solution of a certain D-log equation. And so I'm going to write down the symbols and then explain what they mean.
Yeah, we should have put finite dimensional.
Yeah.
Somewhere.
Finite differential.
Then if
That's type zero.
You mean not-
G
not
K over F is
Finite dimensional.
finite
So to
dimensional.
speak.
Well, so I mean it in any of the equivalent senses of having finite, it's differential coordinating, having finite transcendence degree or finite Morley rank or
Finite
any of
transcendence
these.
degree, finite Morley rank.
Yeah.
The Galois group is a differential algebraic subgroup, right?
Yes.
Yes.
It has to be a finite
So
multivariate
it-
for this theorem.
So when you say finite dimensional, you're not talking about differential dimension?
No,
I'm talking about just transcendence degree.
transcendence.
Transcendence degree of the differential coordinate ring
Finite
is 0.
multivariate,
Okay.
Yeah.
which is a strong condition.
And so basically, it's going to be a solution of some d-log equation of a special kind for some algebraic group G tilde. And now, it's not going to be the usual d-log equation that comes, or that we're used to from Colchin's strongly normal theory, because if it was just the usual d-log for an algebraic group, then that would mean that this is strongly normal. But this is actually a proper generalization. And so
What does D log mean?
I'm going to get to that.
You're gonna tell us.
Yeah. But the point is that keep your intuition from the strongly normal setting, but we're going to tweak a little bit. And that's the characterization. So this is what we're going to get to. I've stated this, it's a bunch of symbols now. It doesn't mean anything yet, but it will mean something, and then we'll understand.
What's that hat on the top of the G?
Oh, that's a tilde. So for some algebraic group, G hat defined over K. So not necessarily over constants. This can be an algebraic group not over constants.
And what is the L here?
L is the Lie algebra.
Oh, the Lie algebra.
Yeah. Yeah. And so, so this is the result. We have about 20 minutes, so I'll try my best to just state everything, and we can talk more about this in the informal discussion after. And so the main result is that so we're going to try to use the structure of the differential Galois group in order to concoct an algebraic group and this d-log equation. So, so right now we're going to look at our goal is to look at finite dimensional differential algebraic groups. To do that, we're going to look at an equivalent formalism of algebraic D groups. And so, an algebraic D group is, I guess, so for just at the level of not groups but varieties, if you have V a variety, then we're going to use the derivative operator on F to concoct a form of the tangent space called the prolongation. And I guess in the case that V is affine, it's, well, we can just write down the coordinates. It's a set of x, u, such that if V is carved out, let's just assume that's carved out by one equation, then this is just the tangent space of the formal derivative of F with respect to the xi's. I guess evaluated at no.
No.
Wait. Okay, I mean it's just the formal derivative evaluated at x. Oh, I guess I chose that notation. Z. So Z is supposed to be a point in the variety, and we evaluate the derivative at Z, and then multiply it by ui. And this should be equal to plus a slight perturbation, where we just differentiate the coordinates of F by the differential operator and apply to Z, and that sum has to equal 0.
So you don't mean the tangent.
Yeah, so I don't mean, if I just taken this away, I would get the tangent space. Or if F is defined by constants, then I get the tangent space. And so what happens here is that, so this tangent variety V is equipped just with the canonical projection. And the point is that a section of this bundle induces a derivation on the coordinate ring of V. So, so a section S of pi is the same as an extension of partial to f of v.
But, for example, if it's a abelian variety, you're not gonna have any f square brackets of e.
So just in the affine case.
Oh.
So just at the level of
Oh, okay.
affine charts.
Oh,
and
okay.
everything. Yes. Yeah. So I mean, you
So
can
you're-
just talk about a sheaf of differentials over, or sorry, we can talk about a sheaf over
You
v
just
and
want
tau v.
f in the local ring. Are you just looking at the tangent space, not the tangent bundle?
We're looking at the tangent bundle.
Oh, tangent bundle.
Yes.
Just the tangent one.
Twisted. I mean, this is the prolongation, the twisted tangent bundle.
What if you
But-
have a singular points and things like that?
So okay, so let's just assume smooth and
But make it a
Okay.
group.
yeah. If it's a group, then it's smooth and
Yeah,
irreducible. I mean, I just wanted to do an irreducible, non-singular case.
okay,
Just for some intuition, so that this makes sense. I mean,
sure.
this is the intuition.
What is F here?
It's
F is our ground field.
Oh, F is here.
Yeah, and so this is just the function, the coordinate ring of
is in
V.
defining ideal group.
Yeah.
I mean, variety. Take generators of the defining ideal.
Yeah. And here I just assumed that it was
Take F goes over the whole defining ideal.
yeah.
I missed that part.
Yeah, I mean, this was just a very simple case, but okay, so an algebraic D structure is essentially this regular section of the tangent bundle. And now, for an algebraic group,
Shifted tangent.
oh yeah, for the prolongation bundle.
Torso.
Yeah, and so for an algebraic group G, tau G is also, you can equip it with the structure of an algebraic group, where you get the group multiplication just by differentiating the multiplication operator like you would in the tangent space, and then adding on at each point this term f partial of g times h, basically. So this has a structure of an algebraic group, and a regular homomorphic section of pi is what we call an algebraic D structure on the group. So GS is an alg D group if S is a regular homomorphic section. And so now using the structure of S, we can define the S logarithmic derivative. So d log sub S from G to, well, the tangent space of the identity, or the tau space of the identity of G, well, it's just a torsor of the Lie algebra, so we'll identify it with the Lie algebra, but we'll just write the coordinates here. And so all it is just we have associated to one of these sections, we have a map eta S to the prolongation space of the identity, just given by mapping GU to E, and then if rho G inverse is differentiation of right multiplication by G1, evaluated at G times U minus the section evaluated at G. That defines a surjective homomorphism for any such section S. And I mean, you have to check that, but so this will define our homomorphism, and then our differential, our d log is just going to be how far this deviates from the actual derivation. So it will be the prolongation map G to tau G to tau EG. And so delta will just map G maps to